All right, let's dive into something pretty captivating, a real debate going on among physicists. It's about how many fundamental constants we actually need to describe the universe.
Hmm. Fascinating stuff.
We'll be focusing on this paper, the number of fundamental constants from a spacetime-based perspective.
Right, and it takes a really unique approach, starting with space-time itself.
It's like instead of just listing all the constants we know, it asks, well, how many fundamental units do you really need just to construct spacetime?
Yeah, and by extension then, to measure any physical observable.
The paper starts by looking at Duff-Okun-Veneziano, who argued that the number of fundamental constants should basically be the same as the minimum number of units you need to express all physical quantities.
It's an idea that makes a lot of sense, especially when you look at modern metrology, like with the SI, the International System of Units. Each base unit there is actually defined by fixing a specific fundamental constant.
But, the SI has 7 base units, right? So maybe it's not the most fundamental system we could be using.
Right, exactly. That's why the paper digs deeper, focusing on the essential tools for any measurement, good old-fashioned clocks and rulers.
What they call bona fide clocks and rulers, if I remember correctly.
Yeah, the idea is that these tools, they have to be reliable, have to give you consistent measurements no matter where you are or how you're moving.
And the paper goes on to distinguish between two types of spacetime, right? Galilei spacetime, the classical one, and then Minkowski spacetime, which takes into account Einstein's relativity.
That's right. In Galilei spacetime, you definitely need both the clocks and the rulers.
Right, clocks are essential for time intervals.
And rulers to make sure everyone agrees on distances, within a given time slice.
Makes sense. But then with Minkowski spacetime, where time and space are all mixed up, well, the paper suggests we might only need one fundamental unit.
Time.
Time, yeah. And they even describe a protocol for measuring distance, but using only clocks.
It really shows how, in a relativistic framework, length just becomes a function of time.
So then what happens to the MKS system, the meter, kilogram, and second?
Well, remember that we can actually redefine the kilogram by fixing the Newtonian gravitational constant, g. So g essentially becomes a conversion factor. And that leads to the MS system, just the meter and the second.
Interesting.
And what's neat is that the MS system reflects Galilei spacetime. We just need those two apparatuses, rulers and clocks.
It's all coming together now.
And even something like the Schrödinger equation, it stays the same in this system, so it's definitely valid.
Okay, so we talked about measuring distance with clocks, but how does that actually work? The paper mentioned Unruh's protocol.
Right. Unruh's protocol shows exactly how to do it in Minkowski spacetime. You see, it all boils down to the fact that in relativistic spacetimes, length can be expressed using units of time.
I mean, it does sound kind of counterintuitive.
It is, and it's not even about the actual speed of light. It's about the fundamental relationship between space and time. Think about it. We already use light years to measure distance. That's distance expressed in terms of time, right? Unruh's protocol just formalizes this idea. It shows that, at least in theory, we can express all observables using just one unit time.
Wow, that's pretty mind-blowing. So if we really only need time, can we just pick one precisely defined unit of time, like the second, based on the cesium-133 atom? Would that be enough for all of physics?
Well, the paper does suggest that as a real possibility. But they also point out that there are other systems, like the Planck system, where you use Planck's constant as the fundamental unit. The important thing is the principle, the idea that you can actually express all physical quantities using a single fundamental unit. It doesn't really matter which one you pick. So we've been exploring this idea that time could be the fundamental unit behind everything. But how does that actually work when we look at specific areas of physics, Like, what about electromagnetism? That seems like it relies on units separate from meters and seconds.
Yeah, that's a good point. We have things like amperes for electric current, coulombs for electric charge. How do those fit into this framework where everything's based on seconds?
Well, the key is to think about constants, like the Coulomb constant, K sub e, as being conversion factors. They're basically a bridge between the conventional systems of units and the single unit framework we're talking about. So instead of seeing K sub e as a fundamental constant on its own, we can view it as a way to translate between coulombs and units that are actually derived from seconds.
Oh, I see. So it's not that the Coulomb constant is some fundamental aspect of the universe. It's more like a translator between different ways of expressing the same physical quantity.
Yeah.
And that allows us to still use those core relationships of electromagnetism, but express them in terms of our single fundamental unit.
Exactly. Take Coulomb's law, for example. The one that describes the electrostatic force between two charges. F equals K sub U times Q1 times Q2 divided by R squared, where Q1 and Q2 are the charges, R is the distance between them, and F is the force.
Right. And in that equation, K sub E, make sure the units on both sides match up.
Right. Now, in the single unit framework, we've already talked about how we can express the distance, r, in terms of seconds. We use the speed of light for that. But what about the charges themselves, Q1 and Q2? They're measured in coulombs traditionally.
Yeah, so how do we deal with that?
That's where the Coulomb constant comes in. It allows us to express charge, which we usually measure in coulombs, using units derived from seconds. It's a shift in perspective, but it means Coulomb's law is still valid. The equation just looks a little different because now the charges are expressed in units based on seconds.
So the underlying physics hasn't changed. It's just the way we're representing it with units that's different.
Precisely. It's like we're looking at the same physical law through a different lens, one that reveals a deeper unity beneath the surface. And this idea of unity goes beyond just electromagnetism, too. We can apply this single unit framework to other forces as well, like the weak and strong nuclear forces. It suggests that the constants associated with those forces might also just be conversion factors.
So are you saying that all of the fundamental forces could be described within this framework based on a single unit?
The paper definitely suggests that as a possibility, but it also acknowledges that there are areas of physics, especially those involving quantum mechanics, that present some serious challenges to this single unit perspective.
Ah, yes, quantum mechanics. Always throwing a wrench into the works. I guess with all its inherent uncertainty and limits on measurement precision, especially with time, it makes you wonder if this single unit framework can really hold up at the quantum level.
Exactly. Like the idea of a bona fide clock, which is so central to this whole framework, might break down in the quantum realm. These ideal clocks, they're supposed to measure time consistently no matter what. But in the quantum world, things just don't behave that way.
Right, because if the clock itself is also a quantum system, it's subject to all that uncertainty too. So how can we be sure it's measuring time accurately enough to be the basis for our entire system of measurement?
It's a real problem. This fuzziness in quantum systems kind of throws a shadow over how precisely we can define units and constants. The paper even suggests that what we think of as fundamental constants might need to evolve as we learn more about the quantum world.
So maybe we need to move away from thinking of constants as fixed, unchanging values and start considering them as more dynamic, something that might even fluctuate or change over time.
It's a pretty radical idea, but it's gaining some traction in the physics community. And the paper hints that this shift in thinking might be necessary, especially when we try to move from classical physics to a quantum description of gravity.
Quantum gravity, right, where general relativity and quantum mechanics collide. I have a feeling our neat little single unit framework might need a serious makeover to survive in that environment.
You're probably right. That's definitely a frontier where everything we think we know about spacetime and fundamental constants could change. The paper doesn't give us all the answers, but it does encourage us to explore how the very nature of constants might be affected by the quantum nature of spacetime.
So instead of giving up on the single unit perspective altogether, we need to find ways to adapt it, to make it more flexible, more able to handle all the uncertainty and strangeness of the quantum world.
Exactly. We've seen how valuable the single unit framework can be, especially with time as the foundation. It helps us reimagine constants, see new connections, and simplify our picture of the universe. But as we push further into the unknown, we have to be ready to refine our tools, to reshape them to match a more complex reality. This quest for a single unit, a fundamental building block for the universe, it's still a driving force in physics. But the path to that goal, it might be more winding than we initially thought.
Well, this has been quite a deep dive. It's really made us question what we thought we knew about constants, measurement, and even reality itself. But it's clear that there's still so much more to discover.
That's the beauty of science, right? It's always embracing uncertainty, constantly questioning and refining our understanding. And as we keep exploring the universe, from the vastness of space-time to the mysteries of the quantum world, we should be prepared for more surprises, more challenges, and ultimately, more understanding.
It's really fascinating, this idea that we might be able to describe the entire universe using just one fundamental unit, time. And we've seen how this framework could help us reinterpret constants and even find new connections in physics. But when we start thinking about the quantum realm, things get a bit, well, fuzzy.
Yeah, the quantum world definitely challenges our classical intuitions. And as the paper points out, those challenges really force us to confront our understanding of fundamental constants, especially as we try to make sense of quantum mechanics.
One of the biggest hurdles we've talked about is this limit on measuring time accurately because of quantum uncertainty. Like if our basic unit, the second, is defined by an atomic clock, and that clock itself is subject to quantum fluctuations. Well, what does that do to the precision of all our measurements?
Right. It raises this fundamental question about whether we can really trust our bona fide clocks. Those idealized tools that we assume measure time perfectly, regardless of motion or anything else. The problem is, in the quantum world, idealizations like that, they might just not hold up. A quantum clock, it's not just passively measuring time, it's a quantum system itself, part of the very reality it's trying to measure.
So it's like trying to observe something that's fundamentally uncertain with a tool that's also uncertain. How do we even begin to build a reliable system of measurement on that kind of foundation?
Well, that's the challenge, isn't it? This inherent fuzziness in quantum systems, it really throws a wrench into our ability to define units and constants precisely. And as the paper suggests, it might even force us to rethink what we mean by a fundamental constant, especially as we delve deeper into the quantum realm.
So maybe instead of clinging to this idea of constants as fixed, unchanging values, we need to start considering them as more dynamic, maybe even something that could fluctuate or change over time.
It's definitely a radical idea, but it's one that's gaining some serious attention. And it might be a necessary step, especially as we try to bridge the gap between classical physics and a quantum description of gravity.
Quantum gravity. That's where things get really wild, right?
Yeah.
Where general relativity and quantum mechanics collide. I have a feeling our neat little single-unit framework might need a serious upgrade to survive in that environment.
You're probably right. Quantum gravity really is the frontier. It's where everything we think we know about space-time and fundamental constants could be turned upside down. The paper doesn't give us all the answers, but it does point us in a new direction. It encourages us to consider how the very nature of constants might be influenced by the quantum nature of space-time itself.
So instead of abandoning this single-unit perspective altogether, we need to find ways to adapt it, to make it more flexible, to accommodate all the uncertainty and strangeness of the quantum world.
Exactly. The single unit framework, especially with time as its foundation, it's been a powerful tool. It's helped us see constants in a new light, discover hidden connections, and simplify our understanding of the universe. But as we explore further, we have to be ready to refine our tools, to reshape them to fit the contours of a more complex reality. The quest for a single unit, a fundamental building block for everything, it's still a driving force in physics. But the path to that goal, well, it might be more winding than we first imagined.
This has been a truly mind-bending deep dive. It's made us question so much of what we thought we knew about constants, about measurement, about reality itself, and it's clear that there's still so much more to explore.
That's the beauty of science, isn't it? It's this constant state of questioning, refining, pushing the boundaries of our understanding. And as we continue to probe the depths of the universe, from the vastness of space-time to the mysteries of the quantum world, we should always be prepared to be surprised, to be challenged, and ultimately to be enlightened by what we find.
Thank you for joining us on this incredible journey into the world of fundamental constants. A world that, as we've discovered, is far more complex and fascinating than we might have ever imagined. Until next time, keep exploring, keep questioning, and keep searching for those deeper truths that lie hidden within the fabric of our universe.